Throughout Chapter 3 of From Zero to Geo, we have been looking at the geometric product, which allows us to multiply vectors. Now that we know how to multiply vectors, a natural question that arises is what do various vector products look like? That is what we will look at in this video. This video is a part of From Zero to Geo, a series where we formulate geometric algebra, an incredibly powerful branch of mathematics, from the ground up. In this video, I want to look at various vector products, what they represent, and how they relate to each other. First, let's look at the product of three vectors. We've already seen this one before, so I'll briefly summarize what this kind of product means. When calculating a product u-v-w, the result is the vector u rotated by the angle from v to w, scaled by the magnitudes of v and w. What would happen if we reversed this product? What vector does this produce? Well, this is still the product of three vectors, so we can do the same thing as before. In this case, we are rotating w by the angle from v to u. This produces the same vector as u-v-w. So here, we see that u-v-w equals w-v-u. In fact, in two dimensions, this is true for all vectors u, v, and w. However, it's important to know that this equation is only valid in two dimensions. Even in three dimensions, the product e1, e2, e3 is not equal to e3, e2, e1. But in two dimensions, this result is true, and it can be useful at times. We can also think of this in terms of rotations as saying that multiplying by vu on the left produces the same rotation as multiplying by uv on the right. Next, let's look at vector sandwiches. By this, I mean an expression like u-v-u, where the vector v is sandwiched inside the vector u. What this represents may seem obvious to you given that we just looked at more general products like u-v-w. Assuming the vectors are normalized, the product u-v-u is the vector produced by taking u and rotating it by the angle from v to u. So why am I making a big deal out of this? Well, there is another useful way to think of it. Notice that here, we have two different vectors coming out of u at the same angle, v and u-v-u. So sandwiching v inside u ends up flipping v across u. Fixing the vector u, we can consider this sandwich product to be an operation on the vector v. In fact, while u has to be a unit vector for this to work, v can be any vector. This operation takes any vector and reflects it across u. In a sense, the vector u is the mirror that produces this reflection. We can go a step further and say that u represents the reflection itself. Wait, what? Aren't vectors arrows? How can they represent reflections? Well, recall that rotors are the product of two unit vectors, but they also represent rotations. It's similar for vectors. As an object, a vector is an arrow, but as a transformation, a vector is a reflection. Note that the way we reflect using a vector is different than the way we rotate using a rotor. In two dimensions, we rotate a vector by a rotor by multiplying them. But to reflect a vector across another vector, we need to sandwich one inside the other. It turns out that when generalizing these ideas, rotations and reflections end up getting applied in the same way, but for now, just think of two-dimensional rotations as being applied differently than two-dimensional reflections. Reflections turn out to be fundamental in geometry, so let's look at a computational example. Let's say we wanted to reflect 3e1 plus 2e2 across the vector 2e1 minus e2. We can just throw these two vectors into a sandwich product and calculate the result. We get this vector, which is way too long. The issue is that when reflecting using the sandwich product, the vector that represents the mirror, which is 2e1 minus e2 in this case, must be normalized. If we normalize 2e1 minus e2, we get the correct result. Notice that even though normalizing introduces a square root, the square root ended up disappearing because we multiplied by it twice. We can come up with a formula for reflecting across non-unit vectors that utilizes this trick. To reflect a vector v across a non-normalized vector u, we need to use a sandwich product involving u hat. U hat is defined to be u divided by the magnitude of u, and since the magnitude of u is a scalar, we can pull it over here. It's much easier to calculate the square of the magnitude of a vector than the magnitude itself, so this form of the sandwich product is sometimes easier to work with. Let's do an exercise. Please calculate each of these reflections. When I say reflect this vector across that vector, I mean to use the second vector as the mirror that the first vector gets reflected through. This exercise is computational, so I will just show the answers in a few seconds. The final vector product I want to look at in this video is a double vector sandwich. For simplicity, assume that the outer vectors are normalized. What does this represent? Well, if we are doing two sandwiches, and each sandwich represents a single reflection, what we are really doing is just two reflections. However, using associativity, we can interpret this product in a very different way. When written this way, we can think of a double sandwich as just being two rotations, where one of them is represented by multiplying by VU on the right, and the other is represented by multiplying by UV on the left. But wait, didn't we see earlier in the video that these both represent the same rotation? They both represent a rotation by the angle from V to U, so the result of this double sandwich is simply W rotated by 2 times the angle from V to U. This shows us that these two very different ways of interpreting a double vector sandwich are actually the same. On one hand, a double vector sandwich is two reflections. But on the other hand, a double vector sandwich is a rotation. Thus, two reflections is the same thing as a rotation. In a future video, this idea will lead us to a fundamental theorem in geometry that is vital to geometric algebra. Before closing out this video, I want to bring up an operation that is surprisingly useful in geometric algebra. Throughout this video, we have talked about several situations where we see a product of vectors going both forwards and backwards. It can be useful to represent reversing a vector product like this as an operation. We will call this operation the reverse, and we will denote it by writing a dagger after what we want to reverse. So the reverse of UVW is WVU, and we can write the double sandwich as the reverse of VU times W times VU. We can simplify this by defining a multivector R to be the product VU. Then the double sandwich simplifies to R dagger WR. The reverse is surprisingly useful in geometric algebra. We'll look at how to calculate the reverse of any multivector in a future video, but here, I want to focus on how to calculate the reverse of 2D rotors. In 2 dimensions, rotors can be written as the product of two vectors. Looking at components, here is an arbitrary product of two 2D vectors. What happens if we reverse this product? Well, it looks pretty similar. The scalar part is the same, and with a bit of algebra we see that the bivector part is negated. This means that to find the reverse of a complex number, you just need to negate the imaginary part. But remember, we can also make rotors using complex exponentials. How do these get reversed? Using Euler's formula, e to the I theta is the cosine of theta plus I times the sine of theta, and taking the reverse of a rotor like this, the bivector part is simply negated. Because the sine is an odd function, we can pull the negative sign inside it. Furthermore, because the cosine is an even function, we can introduce a minus sign inside it as well. The argument of the cosine and the sine is now the same, so by Euler's formula again this is equal to e to the minus I theta. So to calculate the reverse of a complex exponential, we just need to negate the exponent. Because multiplying a vector by VW on the right is the same as multiplying it by WV on the left, multiplying a vector by a rotor on the right is the same as multiplying the vector by the reverse of the rotor on the left. In particular, multiplying it by e to the I theta on the right is the same as multiplying it by e to the minus I theta on the left. Again, these last few equations are only valid in 2 dimensions, so check that you were in a 2-dimensional context before you use them. To make sure you understand the reverse, let's do an exercise. Please simplify the following expressions. In the last several videos, we have been focusing on 2 dimensions. While rotating and reflecting in 2 dimensions is nice, how do we go about doing these operations in 3 dimensions? That is what we will answer in the next video.